Hello. Welcome to Ants Are Everywhere. Today, we're taking a look at an FPGA implementation of a Lisp machine. Why take a look at an FPGA Lisp machine? First of all, we've been slowly learning a little bit of hardware design, Verilog, that sort of thing, starting from a base of not knowing any of it. So we're kind of going down that road. And Lisp machines are fun. They're related to Emacs. If you want to run Emacs on an FPGA, this might be one way to try to do it. Of course, none of the packages will work, but that's a detail. And it just seemed fun. Also, Lisp machines were originally designed for AI. Here's AI memo 528 from some year. That might be 1980. When they still thought they could do AI with much simpler machines than we have today. And the language they wanted to do it in was Lisp. Who can blame them? And so they tried building some hardware. And that's kind of where this design came from, I believe. Here's some documentation for it. It's called UHDL, I think, is the name of the project. Or maybe that's just the name of the site. It runs on this Z-Link Spartan thing. And it's got some requirements that we're going to ignore. And you can add a new board to support it. So let's take a look. I believe it's based on the Catter machine from this PDF. And we're not going to see much of it. And we're not going to understand much of it. But we'll just poke around. So the board should be the boards that it supports. Bus int, presumably some sort of bus. Maybe before I start, I should say that the Lisp machine in question, I believe, is a stack machine. I don't know how quickly to verify this. It's called the Night machine or the Catter machine. Night machine does not exist. How about just Lisp machine? We can bring this up. You can also ask the AIs. Let's ask Google. What kind of processor did the Night or Catter machine have? Okay, so Gemini is saying that maybe the predecessor machine, the Kant's machine, was the Night machine. I believe Night is still on this paper, though. So, wait. I've got too many tabs and stuff. Somewhere, I have the PDF of the paper here. And Thomas Knight is on here. Guy Steele's on here, who's a name I know. I don't know if I know Moon or Holloway, and I believe Richard Stallman was part of the group that decided not to join any of the Lisp machine companies. So first, look at that. That looks fancy. It looks a bit rusty. And let's find out what the Night machine. This is the Night machine, I guess. Okay, so the Night machine is the Khan's machine. And let's figure this thing out about Stallman. Two AI people who were not hired by either I think it means either Symbolics or I think the other one was just called like Lisp Machines or something. Were Richard Stallman and Marvin Minsky. And so on. So Koorosh is asking, what are some other machines apart from stack machines? So Lisp machines, I believe, is a stack machine. Another common type of machine is a register machine. You can look these up. So these just refer to how the CPU, I guess, stores things like variables. So a register has addressable registers. These are subclasses. It gets its name from the use of one or more registers, in contrast to the tape and head used by a Turing machine. And then the stack machine should use stacks. in which the primary interaction is moving short-lived temporary variables to and from a push-down stack. I think this is, they extend push-down automata. I think maybe Forth is several Forth chips. So Forth is a stack-based language, I believe. In simple languages like Forth that lack, local variables, so I guess now we're here. It's also the name of an integrated IDE. So it's a stack-based thing, kind of like Bitcoin. So those are two types of machines. There are other types. There are like subtypes of register machines, subtypes of stack machines. I'm sure there are other fancy machines that are used in VMs, but I'm not sure what they are. So based on the information gathered, they say the Catter machine is a 32-bit microprogrammable processor. This means the machine's instruction set was implemented in microcode, allowing for a high degree of flexibility and customization. And Lisp machines were specifically designed to efficiently run Lisp, and so on and so forth. So does this mean all the Lisp-specific stuff was in the microcode? Yes, that's a very accurate way to put it. A significant portion of the Lisp-specific functionality is indeed implemented in the microcode of the Catter and Knight machines. It's a layer of instructions that the processor executes at a very low level. And it essentially defines the machine's instruction set. In the case of Lisp machines, they were designed to handle things like data type tagging, which I think is used in typing. The data type of a variable is determined at runtime. The microcode would efficiently handle tagging and checking of data types, garbage collection, and Lisp manipulation. So like, how is the microcode coded up and stored? Do humans write the microcode? And if so, in what kind of languages? I don't know anything about microcodes. So control signals. The CPU executes instructions by manipulating a vast array of control signals. And microcodes are, I guess, programmed as control signal sequences. Yes, they write it. CPU designers and engineers are responsible, blah, blah, blah. There's microassemblers. Instead of directly manipulating individual bits, engineers typically use a microassembler. And there's horizontal and vertical microcode. Okay, we're not going to go too deep into that. I guess I will open the Wikipedia article. And I'm curious to see if we can see anything here that looks like code. I don't know. I'll learn about that later. So let's just dig into the Lisp code. Okay, so these are boards. I guess it doesn't really matter which boards it supports. Catter.make, I'm going to guess is some sort of make file. We probably don't need to look at it, but we might as well look at catter.v and catter.vh. VH, I don't know, is maybe some sort of header. Verilog VH file. Headers. Potentially. And we also have wires. The catter4.lisp, this might be the machine code. We have some notes. I guess we might as well peek at the notes. We also have catter4. I don't know if that's newer or older. Here's the net list. This should be the, did we open net list? Yeah, this should be the, like describing the network of chips or closer to the level of electrical components compared to Verilog. I think not quite yet at the physical layout level, but closer. There's an LED controller, which we are going to ignore. MMC, I don't know. DPI is maybe dots per inch. MMC might be memory management something. It might be something related to the video. I'm not sure. Mouse. I guess we'll look at mouse. There's a RAM controller. Might as well look at that. A SPI port. There's some scan code stuff, I guess, for interacting with the ROM. And then, I don't know what ARDI is, but we'll open up some of this stuff. Oh, Arty is maybe the board, because Pipistrello I think is a board. This VGA stuff should be video. And XBus, how about xbus.disk? That should be some sort of bus. And then we have cores. I don't know if we opened up busint, but let's open up busint and no, not boards. Let's look at cores. Cores rhymes with board. Cores. Okay, so we have DP RAM. That's RAM. HC60, I have no idea what that is. IC stuff. PS2. I'm hoping it's the PlayStation 2, but I'm sure it is not. More RAM, some ROM. Here's the UART thing, and whatever US is. So we'll just peek at a couple of these. This is just the counter.make, and it's like how to build it, I think. I'll ignore that. And this is hard to read. Fossil, whatever this, is Fossil its own? I think there's only one L. What's it called? Code stuff? Source control? I think it's a distributed source control thing. A coherent software configuration management system. Okay, it's got all the things. Does it use Subversion? Or is it its own thing? SQLite transitioned to using Fossil for version control over CVS in 2009. Content is stored in a SQLite database so that transactions are atomic. It's not bad. Requires no central server. Okay. So it doesn't seem like a bad design, but these names are unreadable. It would be nice to know what file I'm on in the URL. Or barring that, at least the top thing should be the file name. But I kind of have to figure out that here's the file and here's the file. It's just a little bit confusing. Okay. So we have this module, and I don't know if I can even get this to be zoomed in an appropriate way. Okay, so we have some module catter, has a bunch of input wires and some output wires. The input wires are ext int. We have reset and boot. I don't know what ext means. External, existential. You can also halt. That's a machine thing from Turing machines. We have spy in, spy out. I don't know what spy is doing. I wonder if the README tells me about spy. Where's my search thing? What's going on here, Firefox? There you go. Yeah, I don't know what spy is. There's SP1. SP1, SPI? SPI Spy is an open source SPI flash emulation tool. Okay, maybe something for flashing stuff. DB read, DB write. I don't know what kind of DB that means. Then we have this EADR, MCR. These are presumably some address. It's an output register. I don't know what MZR is. We have memRQ, etc. And the busint. And these all have various sizes. And then we've got an auto wire thing. I think that's potentially some keyword telling it to do auto wire. So Guru says they think the SQLite people wrote Fossil. That's interesting. The SQLite people are very good at what they do, I think. Okay. And so we have a bunch more wires. these are being auto-wired. These are from other things. I guess these are from other Verilog files like cat or ALU and other things. So these are all being wired into this main module. And I guess this is like the God module. We also have debug, whatever I fetches. People don't seem to like descriptive variable names. PDL, PDLA, sinter, I don't know. More spy stuff. SWP is possibly swap, and trap, presumably some sort of trap signal. Okay, and then Y out is presumably YouTube. JK. We have X out and Y out. This might be for video. 11, 15, 19, 23, 27, 3, 31. What on earth? This is 11, 15, 19. I don't understand where these numbers come from, which is, I think, I mean, I'm confused about just about everything, but I would like to know. I'd like to know if there's some, this is some set of integers that's well known. Strongly suggests that you're looking at the description, blah, blah, blah. I could have given it this context, or probably the bit positions of those outputs. So X out 3 would be bit 3 of the output, is that the ALU output is being divided into individual bit signals so that the rest of the CPU can use those individual bits. The specific numbers might be related to specific architecture of the Catter machine. It's possible that it has some internal busing structure that lends itself to those specific bit selections. Okay, and so ALU is what, like arithmetic logic unit or something? Let's try that. Arithmetic logic unit. That performs bitwise operations on integer binary numbers. Okay. So that's straightforward conceptually. I don't know why these things, I don't know why we go, maybe these are bits 1 and 5. Maybe these are bits 1 and 9. I don't know why we decrease in numbers, but I'm guessing that possibly 2 numbers means 2 bits, although it doesn't seem to have 2 bits. So I don't know. Who knows what that's about? Not me. And then we have some wire, which has the BD state in, maybe board state in, and then some parameters like reset, decode, read, ALU, write. These are different, I guess, states. State ALU, state write. I don't know what state ALU means. Maybe it means we're doing something on the ALU and like waiting for it. And then we have a register. I think in Verilog, I learned that register defines like a variable. So state is essentially a variable in the Verilog world. And then wire state read, state ALU. This is more state stuff. We're like wiring up some sort of state machine. This is something about always on the positive edge of a clock. If reset, then we're going to set this. I guess this means set the state to state reset. Otherwise, I guess on every clock positive edge, if the reset signal is not coming in, then we're going to set the state to the next state. And then next state is, I guess, this is maybe computed by this logic here. And if the state is state reset, then the next state is state decode, possibly. This looks like it wants to be a ternary operator with no thing over here. Or maybe the thing over here is the remainder of the statement, and it's just unfolded. So if the state is state decode and the match run, maybe the machine is running, then we'll go into the read state. If the state is state decode and the match is not running, then we'll, I guess, stay in the state decode every clock signal. And if the state is read, we'll go to the state ALU. I don't know how we know what to read. That's presumably stored somewhere, possibly on a stack. And if we're on state ALU, then we're going to go to write. So ALU is this kind of like intermediate stage between reading and writing, which makes sense because that is, does that make sense? That's where the logic is, that's where the bits are being chomped. The inputs to an ALU are the data to be operated on, called operands, is the result of the operation. So there's a variety of input and output nets, which are the electrical conductors used to convey digital signals. Didn't I add this to Wallabag? Is it not telling me that I think I read this before. Not that I remember it. It's a combinational logic circuit, meaning that its outputs will change asynchronously in response to input changes. So you send it some stuff on the wires. It's going to, I guess, compute the things on the output. In normal operation, stable signals are applied to all of the ALU inputs. And when enough time, known as propagation delay, has passed for the signals to propagate through the ALU, the result of the ALU appears on the other side. So it takes some time for the electron pixies to do their magic, I guess. It takes nearly instantaneous time, I would think. But it's non-zero. And then you have to wait, I guess, for that time before you check what's on the other side. And here's some common operations: add, subtract, twos, complement, and, or, XOR, etc. And then there's some bit shifting operations. And perhaps the idea here is that since it seems like we are the only thing between like reading and writing is ALU. So it seems like maybe the ALU is doing almost everything. So if the state is right and we need the MMU state, we'll go to state MMU. And if the state is right and we don't need the MMU state, we'll go to fetch. So we're going to fetch something. And if we're in state MMU, we're going to go to fetch anyway on the next clock cycle. So I guess that means that state MMU just takes a single clock cycle, perhaps. And then if we're in fetch and MCR hold is on, we'll go to state fetch. I don't know what MCR hold is. And then the last thing is we go to state decode. And then we're assigning state stuff here. And then here's the, what? I was going to say instructions, but I control IRAM. I don't know how interesting this is. Okay, but we're doing some stuff here. So catter debug, catter ireg, IOR, and other stuff. Catter source. Okay. It's a bit hard not knowing what any of these abbreviations are likely to mean. But let's take this like state machine looking thing and ask the AIs. So MMU has to be memory management unit, I would think, right? It must be. So this is doing memory stuff. What was this other MCR? Let's ask the AIs. So in this code, what is MCR? What is MCR likely to be? The machine control register. So the this line indicates that the state machine is waiting for a certain condition related to the MCR to hold. Okay, and it says machine control register. So let's look at this. So we do have this SECD machine, which I think is related. Stack, environment control, and dump. But it doesn't say anything about machine control registers. But maybe that's just some register. Oops, I didn't mean to search in Wikipedia. I meant to search for... Can I copy this? Let's search on Google. A control register refers to additional registers visible only in kernel mode that provide access to mode control information and serve as a safe operating space for the operating system. So maybe just control register. So maybe this is just a register that's part of the control system. Is a processor register that changes or controls the general behavior of the CPU. Okay, so this is just like a, I'm going to think of it as mode information for the CPU behavior. Okay, so let's move on to some other files. This is just some header, I think, but it has like no information, no code that we care about. Here are some notes. I don't know. This is HTML, it looks like. So catter clock 1 master clock 2 master clock distribution. ICTL is IRAM control. I don't know what the I stands for. IWR is instruction write register. I don't know why this couldn't be in the code. I don't know if there's efficiency reasons for having bad variable names or if it's just preference, idiomatic preference. PCTL is PROM control. And there's debug instructions. IREG is the instruction register. IOR is the inst modify OR. I don't know what OR is. O register. And then source is source test or decode, op decode. And then we have some memory, more memory stuff, but we'll keep this open as a dictionary and I'll put it all the way to the left. Okay. So moving along. Here's catter4.lisp. This is actually Lisp now. This is a wire list of all the wires for each schematic page for the catter4. Commas have been replaced with underscore, and the quoted symbols have been hyphenated instead. What? So we're going to define catter graphviz dump. This is dumping a graphviz visualization of something, some graph, presumably the graph encoded Lisp-wise in here. And you're going to format it as a digraph. And map car, you're going to map some lambda wire. This is like, I guess, formatting the wires. Okay. And this seems to be essentially just generating a file for, I guess, possibly controlling the graphviz stuff. And we're going to just do Lispy stuff. This could be, I think, in like JSON, but it's in Lisp. So we're going to define some catter wires, like ACTL, which is what? Something control? A control. What is A control? I still don't know, but it has some stuff. This is maybe the way to think of this is as a what's the word? It's a graph representation where you have the node on the left, and then this on the right is all of the other nodes it's connected to. And so I guess ACTL. I don't know if I think this is directed. Yeah. Okay. So the ACTL node should point to APAS2, IR34, all of this stuff, DR5B, and so on for ALATCH and AMEM. So list versus adjacency list. I don't know why I was blanking on that. So this is, I think this is just some adjacency list. Let's see if A control ever appears on the right-hand side. No. Does IOR appear on the right-hand side? No. It seems like, or maybe this is, this might be like the name of a bunch of wires. I'm not sure. Let's see if A pass 2 appears on the left. Let's just ask. So does this encode an adjacency list? And if so, what's the format? Okay, so the pages, these are pages. Okay, so the first element of each pair is the page, ACTL A latch. A list of pairs. Each pair represents a schematic page and its corresponding wires. Okay. I guess by schematic page, it means a page of the schematic. And the pages act as the vertices of the node, and the wires listed for each page represent the vertices that are adjacent to that page. The code then turns this data. All right. The page.wire, the page symbol. So ACTL is a vertex, and these are the wires. Okay. No, these are the vertices that are adjacent. There's a directed edge. So, okay, so then why, shouldn't there be, in that case, should there be vertices that appear as pages or and pages that appear in vertex lists? Otherwise, it's a pretty unusual directed graph. The graph is representing a specific kind of relationship, a hierarchical or data or flow-oriented structure, rather than a general purpose network. It is likely representing the flow of signals or connections from control pages to individual wires or components. Okay, so this is the control structure. I guess think of it as control signals emanating from a control page and going to activate specific wires. It does not appear. Okay, so according to Gemini, that this is like a control signal that like activates wires, and I'm going to think of it as putting electrons on the wire, but that may not be true. Okay, so and then here's the net list, and it's got parts, and then I don't know what P1 through P15 are, but these are like connectivity stuff. So for example, this part, A something or other, 21. P1 is clock, 3D, W adder 4, etc. This is maybe the negation of the signal that's going from ADR4A, and so on. And this is something I think that should be computed from the Verilog code by some sort of compiler processor. And it's probably not worth trying to figure out exactly what's going on in it. And then here are the Cater4 wires. And it seems like Gemini was right. We have page ACTL, and it has this stuff. This might be just generated from the Lisp code. It doesn't seem any less readable. It doesn't seem any less readable than the Lisp code, but I guess it's longer. harder to grep. It's harder to like process this and say, is APAR connected to A1? So I guess in that sense, the Lisp notation is better. Here's the MMC.v thing. We have this timescale, 1 nanosecond over a picosecond, I believe. And what? We've got some output registers. What did we decide MMC was? I'm not sure we did. What is MMC likely to be? Microsoft Management Console, centralized management. No. I'll say in the context of the Verilog Catter thing. It's highly unlikely to be Microsoft Management Console. Thank you, Gemini. Memory management control? Is that different from memory management unit? Is used in conjunction with signals to blah blah. Is that different from MMU? So the memory management unit is the hardware component responsible. Okay, and the control is the control logic. Okay, that governs the behavior. All right, I'll buy that. And we do have this dictionary. Does it say what it is? No. Okay. At any rate, we've got some registers, some input wires for a command, which is, I guess, 48 bits wide. That's kind of an unusual size. What is the word size of the Catter machine? So let's see. So symbolics lengthened the word to 36 bits and Lisp to 40 bits. So I'm not sure this, I don't think this is connected to the word size. It's just some wires that are going in. We have some parameters like frequency, rate low, bit width high. This seems like it could feasibly be related to memory management. We have some bit shifting, some bit sample, bit 8, bit 100, and so on and so forth. And then here's some logic. On the positive edge, we do a bunch of stuff. The begin of auto reset for uninitialized flops. I don't know if a flop is different from a flip-flop. Okay, so that looks like memory stuff. This looks like mouse stuff. And PS2, PS2 I think is like the mouse connector from the days of old. It's like a circle-y thing. This. And it's color-coded to prevent you from doing what? Confusing two connectors that look alike. Okay, so this should be mousy stuff. We should see some X and some Y. Poll. So maybe we're going to poll some stuff. And we should see some X. Yeah, okay. So output Y or X and Y. So something goes in and it's going to output X and Y, and I guess that goes to the screen. Oh. I missed this. Koorosh is saying the virtual address size on x86-64 machines are 48 bits as well. Oh, that's interesting. These are the virtual address sizes, and then I guess the MMU converts them to addresses. I'm not checking it because I'm checking up on what you're saying. I'm just seeing if I can get a resource on learning more about it. Okay. 48-bit virtual address space, so we get 2 to the 48 bytes. Whoa. Of memory. How do we go from bits to bytes? Oh, okay, so each one represents a byte, I guess, right? Let's read that. Cat proc CPU info grep 48. All right, I'll do it. Uh, hmm. What if I cat dev u random and pipe it into my... I really hope Linux prevents me from doing this. Okay, good. Whew. That was going to end the stream. Okay, so and then we have some state. What are we? This is the mouse. We have some state machine, and I'm not going to really look at the mouse. I'm going to see if we can get anywhere closer to the microcode. Here's RAM controller. In a world where I hadn't spent so much time looking at the other stuff, I would look at that. This is RT. I think RT is maybe related to the boards. I think there's like an Arctix board, but maybe this is different. Arctix 7. Okay. RT7. All right, I think this is a board thing. We'll ignore that. This is also specific to RT. Here's XBus disk.v. I'm not sure what XBus is. Maybe it's a standard. There's MBus on Spark. And what about XBus? Okay, XBus is a packet switched bus used in the Spark server. Okay. So I'm hoping this is the same. Otherwise, there's a name collision here with XBus. This is a simplified Trident disk controller. Much of the error checking, parity, ECC, etc. is missing. Oh, good. So that's fine in that this is a project to kind of like recreate something from the past, but you, I guess, wouldn't use it in production because your disk stuff might be off. Expects the block device to provide 1024 byte blocks with 16-bit interfaces. Okay. So I'm at least at the point now with Verilog that I can tell on average better than a coin flip what a file is supposed to be doing. That's a low bar, but it's better than where I was before. Bus int is the bus interface. And this is, I guess, what passes as a comment block in Verilog. And we have, so the inputs are address, which is now 22 bits, the data in, which is 31, for a total of 42. Is that where we decided? 48 is what the, and then okay, 42, and then rec and write. That gives us 48. I don't know if that's a coincidence or that's just how it works. And then we have data out ACK. Maybe ACK because we're like doing something like packet switching and we have acknowledgements. And then we have some SDRAM data in, which is 32 bits. Data done, whether we're ready, some address output, and some data out, and so on and so forth. Okay, so that's good. I'm going to move along. Here's a header. Common tasks for the bus interface. Task wait for by done. Begin while ACK is 1 at the positive edge of the clock, and then end. So we're going to stay in this loop as long as ACK is 1. And then I guess ACK is 1 as long as something is being accessed. And so when it's 0, we're done. And then bus read is going to take as an input A and output something called out. And then begin on the positive edge of the clock. We're going to write 0. We're going to set the variable write to 0 maybe, set request to 1, set address to a. I'm guessing these might not just be setting variables, these might be like sending these signals on the wire. I'm not sure. Wait for by done is this method up here. And then we're going to display some stuff. I don't know if this is for debugging, but then we'll set the data out to out. So data out, I guess, is what came in from the thing we're talking to. Anyway, I guess we're going to send that back out, and we'll set rec to 0. What is the positive edge of the clock? Is the same as the front as back? I don't understand this question. For the front or back? I don't understand the question because I think that you know way more about this than I do. So that leads me to believe that you are possibly thinking at this at a deeper level than I am. But my understanding, as bad as it is, I don't know why I looked for a clock. My understanding, as bad as it is that we just have some oscillator, which is doing electro oscillation things like a piezo thing or whatever, and the positive edge is just 1. But it may be that it may be that it's a lot more complicated than that. And maybe it may be that the oscillator is somehow like processed into a cleaner clock, which you would kind of hope it is. So we have a regular D-latch response. So far, we've studied both SR and D-latch circuits with enable inputs. The latch responds to data inputs. Is this about clocks? This is about flip-flops. Let's see if Wikipedia will find anything. Signal edge. A signal edge is a transition of a digital signal from low to high or high to low. So, okay, so it's not just where it's 1, which is kind of intuitively what I was thinking of, but because we have essentially sampled this, the positive edge is where is this blue line, where it started low and it's becoming 1 for the first time. Like if I press a key on the synthesizer, beep, the positive edge is when I start the beep, and then the negative edge is when I stop the beep. Something like that. And then a flip-flop, it says, is an edge-triggered circuit. And then we have the rise time. And this might be kind of the rise time might be like the, on this graph, I don't know what it is, but where it says undefined, basically when you're in this section, like if you can imagine a really old electronic circuit that took a while to get, maybe like a vacuum tube that was heating up, there might be this intermediate period, I think is what's basically going on. All right, this is bus interface. This is more RAM stuff. I only have a few more minutes. I can see if I can get somewhere that looks a little bit Lispy. I was not really expecting anything to look too Lispy because this is supposedly mainly a stack machine, although nothing looks too stacky to me yet either. Here's some core IC 74181. Let's see if this is like a chip or something. So that's the AMU. Maybe you can buy one. This should be a fairly modern chip because this is not an old Lisp machine. This is a Lisp machine that runs on a real FPGA. Okay, and so let's see if we can just jump to the this documentation. Where's the... How do I get home? Homepage? Okay. Oh, maybe I want files. So boards, fossil settings, cores to do. Let's try this. What if I took a screenshot? Can I do that? No? I'll say here's some files and folders from the Catter project, which, if any, are likely to contain microcode that seems Lispy. So Catter4.lisp, but that was the one that had the okay, that's the one that had the graph essentially, right? Catter4.lisp. Let's grab this whole thing. It did say that microcode was basically wires and stuff. So here's the Catter4.lisp. Does this look like microcode? Oh, you know what? It's not gonna let me copy the whole thing. Okay. Is within the UHDL files. Okay, okay. So it's maybe in the files that name the boards that I skipped over. So we have this Verilog file and this RD file, and we'll see if there's anything that looks microcoding here. Maybe in common. Idea. Okay, so common top level module for the LM3. Idea is to have generic code for the actual top level module. Intent would be to skip wiring, a bus hinge, etc. And here is some XML. What if? What in the world? What am I supposed to do with this thing? I cloned the repo using Fossil, but I guess I don't know how to open it. So I'm not going to try to figure that out live on air. Can I search in the web page? Maybe if I log in. I don't know. I just don't know. So wires, Catter TB. Here's files. Here's forum. Is there anything in the wiki? No. Let's try going back to the home page and seeing if it tells me. So I did that. Let's try this open operation. There we go. Cool. Let's try looking for CDR. How about cons? We have const. We have some XML stuff. Let's try this one more time. Okay, there we go. So maybe this netlist thing. Extracted from suds file bodies, blah, 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 title one cons, flags conditional. I don't know. Is there a cdr? There's C drive. How do you spell cdr? What if you just search for microcode? To do microcode control, microcode submachine stack. Okay. We have cdr in space. Are these all cdr things? I don't know if cdr is the name of the machine or what. But we have SPC. I'm not sure if I'm going to find anything that looks microcodey. What if I just do Lisp machine microcode cdr and just look on the internet? So this looks like a good description, but do we get to see anything about microcode? It runs Lisp quite directly, not in the sense that the processor runs Lisp directory at the hardware level, but I'm also not sure what this means. If you do not see the microcode as you do not see it in modern processors, then it is also valid to say that this machine runs Lisp natively, as much as a modern processor runs its machine code natively. Yeah. I don't know how to find the what the microcode looks like. I don't even know if it would be interesting to look at. The microcode store is writable, so it's continuously developed as part of the Lisp machine. Oh, maybe I should try instruction set, which has several Lisp primitive instructions. So how about Verilog instruction set? And how about we also grep for instruction set? What about example? I don't know. I don't know if these example designs are anything useful. Are these F lists useful? Implement.bat, implement.sh. How do I search for a parenthesis in grep? How about defun? Yeah, I don't know. So I don't think I'm going to be able to find any microcode. Oh, a relatively late version of the Lisp machine microcode is here. Well, look at that. Okay. Oh, this is like a separate repo. That's why I can't find it. Okay. I don't know. I don't have more than like 3 minutes, but we'll like look at a couple of these just kind of randomly. Here's macro code. All right. I don't know what this this file format is, .mid, but mmimem, some number, and pdp11. Something about pdp11's unibus adder controlled by the map. That's like a comment. And we're doing stuff. Cn usp sets a skip in all this sort of stuff. So this looks like maybe this is the like raw assembly here, and then these are maybe it's defining like these routines that will be the stuff that you actually compile to. Garbaging unibus map. So there should be like garbage collection. I think is possibly going to show up in the microcode, but I don't know. This I don't know what this is. This looks like we're still down in the. I mean, this is looking more and more like microcode. This is binary data. It's not even going to show it to me. Assign chaos source address. These raw numbers, I'm assuming, are meaningful to the hardware in some sense. There's also something about jump 0, halt, cons, wild transfer to 0. Don't get screwed or clobbered by something or other. Yeah. Okay. So somewhere in here, if we like looked this closely, I think we would begin to see a picture of what the microcode looks like. Error table, and so on and so forth. It seemed like we didn't find it because it was just in a different repo from the same on the same page. And that's really all I have time for. Did we learn anything? I don't know. I don't think I'm more ignorant than when I started. I don't know if it's safe to say that I'm less ignorant than at the start of the hour. But that's that. Thanks for watching.